All right. So this is a mock interview for the software engineering intern role at LinkedIn. This mock interview will contain two coding exercises that will both be walked through and solved. So I'm going to go ahead and start by working with the first coding exercise, and I'm going to go ahead and copy and paste it in. Yeah, that should be the right one. So this problem has to do with finding the lowest common ancestor of a binary tree. So you're given the root of a binary tree, and you have two nodes, two arbitrary nodes. We can call them P and Q. The goal is to return the lowest common ancestor, which is the lowest node in the tree that has both P and Q as descendants, where a node can be a descendant of itself. So there's already a predefined tree node class, and each tree node will contain a value. It'll contain a left variable, which is another tree node, and it'll contain the right value, um, which is another tree node representing the right node of the tree. So in this situation, um, it already passed left and right already passed none by default. And what that means is that there isn't essentially a subtree available. If it's none, there is no subtree, or there is no left node, which means there is no subtree. And right, same thing as well. There is no subtree, there is no root node, or at the end of the day, there is no subtree if it's none. So walking through the first example, in the first example, the corresponding tree would look like this for root. And we are given two arbitrary nodes, P and Q, which in the first example, they are 5 and 1. And the expected output should be 3, because 3 is the lowest common ancestor between 5 and 1. And that makes sense because obviously with the definition of the lowest common ancestor, we know it's the lowest node in the tree where both P and Q are descendants. And the lowest node in the tree possible that has 5 and 1 as ancestors is only going to be 3. In the second example, same tree, but this time the nodes are going to be 5 and 4. And the expected output should be 5 because 5 is a descendant of itself. We said that the LCA is the lowest node where P and Q are descendants of that node. So a node is allowed to be a descendant of itself, which makes 5 the expected output, and 4 is the 4 is a descendant of 5. The third example, there is no tree for it, but there's 1, and then it's just 2. And the expected output should be 1. Kind of the same situation as example 2. A node is allowed to be a descendant of itself. So the lowest common ancestor will be 1 that contains both descendants of P and Q, which are 1 and 2. All right, so kind of a very kind of an okay problem. The best way to start this is by doing a recursive approach, where we recursively check each subtree in the root tree. So first things first, in order to be able to do the recursion, you need to have a base case. And that base case will essentially check if the root node exists. There are two of them in a way, but they both seem like they will need to return the same value. And the first case that exists is if there is a root node, we need to check. So check if there is a root node, because we won't be able to do any recursion if the root node is none. And if not there, simply return none or root. It makes more sense to return root. It makes more sense to return root because root will already be none, and we can just simply return that. So we can just return root. Second thing we need to check is we know that a node can be a descendant of itself. And when that happens, that means that the root is essentially equal to P or Q. So we need to check if a node is a descendant of itself, which means root is P or root is Q. And then we would just simply return the root. Then from there, we can do the recursion on the left and right subtrees. So do the recursion on the roots children. left and right subtrees. And I'm going to put Python comments so that way it doesn't interfere with the Python syntax. And then while we do the recursion on the roots left and right subtrees, there are three possible situations that can happen. The first situation is if we find P and Q in the left and right subtrees. So if the left subtree returns P, for example, and the right subtree returns Q, we know that we found P or Q in both subtrees. So both subtrees essentially return a node. I'm going to call them left and right because that's what they are. Both left and right subtrees return a node. And when this situation happens, we can just return the root because we know that the root will be the lowest common ancestor possible. And then, well, technically, it's not really three possible situations. It's two, because the second possible situation that can happen is if either left or right subtree return a node. And when either one returns a node, we essentially just bubble up. And bubbling up is essentially returning back to the parent recursive call. And in that example, if I have 6 and 1 in this situation, when I go through 6 and I go through all the way to the left subtree, and I find 6, which is in this situation P, I already returned 6, and then I can bubble up to my parent recursive call, which is on the subtree containing root node 5. And then I would bubble up to 3, and then 3 finds 6 and 1, and then you would return 3. So kind of like that in a sense, where you would just have to bubble back up to the parent node. So that is essentially the code in a sense. This is going to have a runtime complexity of O of n because we are traversing through the node n possible times. And it'll have a space complexity of O of h because the recursion is happening of a tree of a height h. So we're going to go ahead and start solving this problem. I'll be solving it with Python. So we're going to be calling this the lowest common ancestor. And this function will take in the root node, and it'll take in a node P, and it'll take in a node Q. And the first way we start is we have to check if there's a root node. And we check that by saying if not root. That checks if there is no root node. We also have to check if the node is a descendant of itself, where root is P or Q. And since they both return the same result, which is root, we can say if not root, or P, or root equal P, or root equal Q. And in that situation, we return the root. All right, the next thing we need to do is we need to do the recursion on the root's children, the left and the right subtrees. So we're going to let left be the left subtree, where we do the recursion, which is lowest common ancestor, where we pass in the left subtree. And we pass in P and Q, because those are still the nodes that we need to check for the lowest common ancestor. The next thing we need to do is we need to let right be the lowest common ancestor with another recursive call where we pass in the right node, and we pass in P and Q because those are the nodes we need to find the lowest common ancestor of. And then, like we said, two possible situations that can happen. The first thing we need to check is we need to check if the left and right subtrees both return a node. And that's just simply checking if left and right both exist, right? We know that our LCA function, our recursive call, will return us a root, and it will return us a root when there is essentially a LCA. So if both of them return a node, then we know that we can just simply return the root because that root will be our LCA. So in that situation, if left and right, we're able to just simply return the root. And then if either one returns a node, we bubble up and we return back to the parent node. So we do that by returning left if left exists, otherwise we return right. And that is the valid solution. All right, heading into the second problem, let me go ahead and copy and paste this problem. So this problem is called word break, and you're given a string S and a list of strings called word dict. And you need to determine if S can be segmented into a space-separated sequence of one or more dictionary words. And you can reuse the words from the dictionary multiple times. So in the first example, we have the string LinkedIn and the word dict linked and in. And the expected output is true because you're able to segment the word LinkedIn into two separate words, linked and in, separated by a space. And both of those do exist in the words dictionary. The next example, you have the string apple, pen, apple, and the word dict apple and pen. And the expected output is true because you're able to segment it as apple, pen, apple, and all those words exist in the word dict. In the third example, cats and og, with the word dict cats, dog, sand, and cat, the expected output is false because no valid segmentation exists in a way where you can put spaces so that every single word that was segmented exists in the word dictionary. And then finally, with cars, the expected output is true because you can segment it into CA and RS, where both of those substrings exist in the word dictionary. CAR and S wouldn't be a valid segmentation because even though car exists in the word dictionary, S does not. And yeah, those are the constraints. The length of the string won't be less than 300. The length of the word dictionary won't be anything more than 1,000. And the length of each character in the word dictionary won't be anything more than 20. And it will always be lowercase English letters. All right, so the first thing that comes to my mind when solving this problem is it's really a bunch of overlapping subproblems because you need to figure out each time you add a character to your string if you can add a space in between. So the way you would do this is, for example, if I had LinkedIn as a string, I would first need to check if L could be space segmented. And it can't because it doesn't exist in the word dict. And then I need to check if I, and then N, and then K, and then E, and so on. So because this is a bunch of overlapping subproblems, the best approach is to use dynamic programming. And you use dynamic programming where S at I, so everything up from S to I, is a valid segmentation. So the way I would first start this problem is I would first need to be able to convert the word dict list into a set. And I'm going to go ahead and put some quotes around these as comments. The reason why I need to do this is it's important to check ownership because an important part of this problem is when we have an overlapping segment, if we need an easy way to check and see if it exists in the word dictionary. And the easiest way to have that O of 1 lookup is to convert the word dict into a hash set. So we're going to convert this into a hash set. The next thing that we need to do is we need to populate our dynamic programming array. And this DP array will contain the state at which a word can be segmented. So contain the state at which the word can be segmented. So this means that DP at I will either be true or false depending on if the word at the current index from S to I can be segmented. Equals S to I can be segmented. So the next thing that we need to do is we then need to check if the string segment we got exists in the word dict. And if it does, we update the state of our DP array to be true. Because in our DP array, each one contains a state whether the word can be segmented. So we know that if it exists, we know that the string can be segmented, and we update that state of our DP array to be true. And then finally, we would return DP at the end of the string, because DP at end tells us whether the full string can be segmented. That is what we are storing. We are storing the situation in which the entire string can be segmented or not, and that's what DP of n will store. So this entire approach will have a time complexity of O of n squared, because I first need to be able to get the prefix or to get the substring, and then I need to be able to have another loop that validates if that is a valid segment. And this is then a space complexity of O of n, because our DP array will store a list that contains our states up to n plus 1 times. All right, so I'm going to go ahead and start coding in this problem. So the first thing I need to do is I need to define my word dict, or not word dict, word break, and this will take in a string s, and it will contain a list called word dict. So first things first, we need to convert the word dict list into a hash set. We're going to call this word set, and we're going to make this a hash set containing word dict. The next thing that we need to do is we need to get the length of our string, and I want to make this a consistent variable. So that way, if anything changes or anything kind of modifies, we want a consistent length. We're going to be using the length of the string a lot in this problem. So it's best to make that its own variable. After that, we then need to populate our dynamic programming array, or DP array. And in this situation, we know that the DP array contains the state at which the word can be segmented. So DP is going to be false times n plus 1, because it's going to store the state n plus 1 times. I forgot to add, we need to add in our base case. Our base case is essentially an empty string in this problem. And an empty string will always be able to be segmented into a space. So let empty string be true in this DP array. So let DP at 0 be true. So we're going to let DP at 0 be true, because we know that an empty string can be segmented. That's what's going to allow us to start the segmentation process of a string. After that, the next thing that we need to do is we need to loop through a string. So we need to for I in range. We're going to go from 1 to n. So that's going to be able to help us get our segment at a time. It's going to get each substring from the prefix at a time. Then we need another inner loop that actually validates that process. So this outer loop is going to actually get li can. Suppose that the string is linked in. We need to actually validate that these are words that can be segmented. So in order to do that, we need another inner loop. So for j in range, we're going to go through I. And like we said that DPI is the state at which, let me write a comment here, but I'm going to kind of reiterate saying that DPI is a state at which S from everything up to index I can be segmented. And if it can be, it's going to store true. Otherwise, it would store false. That means a string can be segmented if everything for up to j can be segmented. So that means string can be segmented if everything, I guess you can say sj exists. So I guess another way to make it make more sense is dpj. We know that dpj is a state at which from string s everything up to j can be segmented. That's what we're storing in our DP array. So we first need to check if dpj is even a thing. And then we need to check if s from j to I is in the word set. And the reason why this is important is because we can't populate DPI, or we can't set DPI to true if everything from j to I is in word set. This essentially is a way to validate that our string exists in word set. Or it's essentially a way to validate that the string can be segmented, and we first need to check if the initial state is true, and then we check if everything up to the original index I exists in the word set. Um, and if this is the situation, then we know that dp of I is going to be true, and we know that we can immediately escape from the loop because we no longer have to check each split from everything up to I. What this is doing, to kind of reiterate, is that it's checking between each and every split. So if I have linked, I then need to run another loop that validates that that exists. So I'm going to start with 0, and we know with dp0 it's an empty string, so that's true. So we know that there is already a state that is valid that we can do the splitting on. And then we also check if everything from 0 to 6 um, exists in word set. And in this situation, it does. So we know that DPI, we can set that to true, and we can continue going on and building our um, string. So once that's done, that pretty much is everything. We then need to return the final state in our DP array, which is just DP of n. And that is pretty much the solution to that problem.